I'm going to make a wild guess here and assume that most of you at this point in your educational careers have made quite a few graphs. Most of those graphs were probably done in a math class, so I'm going to imagine that you're probably not too enthused about being assigned to do yet more graphs in chemistry. Well, I want to take some time here to look at the differences between graphs that we construct maybe in a math class and how they differ from graphs that we do in science, because there are some major differences here. One of the major differences is that in science class we're almost always dealing with real-life data that has errors and imprecisions in them, and they're not entirely reliable. A lot of times in math class the numbers that you're given are very exact, and there isn't much uncertainty in some of these numbers. Not all the time, but a lot of times that's true. So I want to take a moment here to look at those differences. First of all, let's think about the reasons why we make graphs. One of the reasons is that we want to present information in a visual way. And in the real world, you might be asked to make graphs to present to, let's say, your boss. Suppose you're plotting the profits of the company over the past year. It makes sense to put that in a graph because it's just a lot easier to see if profits are going up or profits are going down. And when you do this, you want to make your graph, as neat as possible. You also want to make it large so it's easy to see. So when you give that graph to your boss, they don't have to squint or try to figure out what's going on. So if you look at this graph, you can see that I've made it as large as possible. I've chosen a scale on the X and Y axis that allows for this graph to basically take up as much room as is possible on the page. Also, I've tried to make things very neat. I haven't cluttered it with lots of numbers, and I've also labeled my axes. Okay, so after you've done that, the next thing to do is to begin to plot your data. So we make different points. In this case, we have two sets of data for pre and post 1982 pennies. In this case, let's say that the pre pennies are in red and the post pennies are in blue. When you plot these data points, you're going to see that they don't exactly line up perfectly on a line. So, what do you do here? We need to draw a line through these points, and it needs to represent the fact that the pennies basically are increasing by a set amount each time, but not exactly the same each time. And there's fluctuations and variations in these data points. So rather than connect the points dot to dot, we're going to draw a line of best fit. A line of best fit is basically a line which seems to go through the majority of the points as best as possible. At this point, it's just going to be kind of eyeballing that. Later, I'm going to show you some equations and some ways of calculating the line of best fit, which is a little bit more sophisticated. But at this point, the major idea is to try to get the line to go through as many points as possible, or to try to have sort of an even distribution of points above and below the lines. Now, if you look at these two lines that I've drawn here, you'll see some major differences between the data that we have for the pre-82 pennies and the post-82 pennies, which are, again, in blue. First of all, there's kind of an outlier point, so I'm kind of ignoring that one because it's really out of whack. And if you recall, there was something that we did in the lab which caused that to happen. So I'm sort of ignoring that with a red line. With a blue line, you'll notice that the data points are kind of all over the place. And so in this case, we want to try to draw a line that, again, is the best line we can that goes through these points. Another thing you'll need to notice here is when you're drawing the line of best fit, you only use data points. So, for example, in this case, don't put your ruler on the origin, 0, 0, and pivot that through your data points, because we didn't really measure anything at 0, 0, and so you can't assume that that's necessarily going to be a data point. And if you recall, in this lab, we did something that affected that as well. Okay, so what's next? The next thing we want to do is try to determine the slope of the line. Turns out that the slope of the line here represents something fairly important. Now, when we do this, you want to choose a point that's on the line of best fit and is not a data point. So we specifically are looking for points that are on the line and not data points. Now, to make your life a little easier, it's always best to try to find a point that intersects the horizontal and vertical lines of the graph paper and your line of best fit. And I've chosen 2 points that you can see here that do that well. This just basically makes your life a little bit easier. Now we're going to draw what's called a slope triangle. So the slope triangle is drawn by drawing lines, horizontal and vertical, from the points that you've chosen. This creates an intersection, which is a triangle, and so it's called the slope triangle. You remember from math class that the slope of a line is defined as the rise divided by the run, or the change in y divided by the change in x. Now you can find that by looking over here on your slope triangle. The line in purple shows the change in y. But to figure out exactly how long that is, you need to look over at the y-axis. The line in purple represents the change in y. To get it, or to get that value, we need to take the whole length of that line, shown in green, which measures 30, and subtract from that the orange line. The remainder would be the delta y. So, the green line is 30 in length. The orange line is 14 in length. Notice it's not 12. You have to be careful about just looking at the squares here. You have to figure out exactly what does each square represent in terms of the mass in grams, and not just as units. A lot of kids will just simply count the squares, and that doesn't work. So delta y is equal to 30 minus 14, and that gives us a delta y, or a rise, of 16, and it's 16 grams. Remember that this represents an actual measurement in mass, not just 16 units. Now we're going to do the same thing to find the change in x, which is called the run. Again, we're going to look at the larger value here, which is 12. And now we got to figure out, well, what's this lower value reading? Well, to do that, you need to look at the scale again. And I chose a pretty awkward division here. So I have actually 5 divisions between 2 milliliters. So to figure out what each little division represents, I take 2 divided by the number of divisions, 5. And that gives me that each division, or each line on that axis, is 0.4. Now there's 3 of those little lines, so that's 1.2 added to 4 gives me a value of 5.2 for the intersection of the bottom part of that line, shown in pink. Now the delta x is going to be equal to 12 minus 5.2, which is 6.8. And again, that's 6.8 pennies. The slope of the blue line here is going to be now the 16 grams divided by 6.8 pennies, or 2.35 grams per penny. Now this is the first thing to realize about a scientific graph. The graph here, or the slope of that line, represents something real. It represents the average mass of, in this case, the post-1982 pennies. That's the grams per penny. That becomes important later. The slope again represents a real value, the average mass of the pennies, taking out inconsistencies between the pennies. Okay, so let's look at some other things that these graphs show us. If you look at the blue line here, first of all, again, the slope represents the average mass of those pennies, taking out the inconsistencies in the data points that you see. Notice that we find the slope of the line of best fit and not points from the data. If you had done that, for example, between the 2 points shown, the slope would be very much different from the one that we have. Now let's just look at the red line and assume that the slope of that line is 2.8. Again, that's 2.8 grams per penny. This shows us that the pre-82 pennies are heavier than the post-82 pennies. By the way, don't use these values in your lab because I just kind of made them up, and your data will be very different from what you're seeing here. Okay, so what else do these graphs show us? Well, let's just clean this up and look at the graphs once again, and just look at the lines themselves. Again, imagining that you're giving this to, let's say, some busy people, and they want to get information quick. What can we tell about these graphs? Well, if you look at the y-intercept where the red line is hitting, you're going to see that it hits at the y-axis. and that really shouldn't be. When there's nothing on the scale, there shouldn't be any reading at all. It should read 0. So if we look at a graph, even if we haven't done the experiment ourselves, we should generally look at where it's hitting at the y-axis. If it doesn't hit at the origin, it may tell us that the graph that we're looking at is not accurate. If you look at the data points, particularly on the red line now, you'll see that the majority of those land on the line of best fit. When that happens, we say that the line is precise. Now you'll notice in this case too that there's an outlier which is not precise. Now it's strange that all of our data points lie perfectly well on the straight line, but one of them doesn't. If you recall from the lab, we put a couple of plastic pennies in there, and that would be a couple of points that were entirely out. Sometimes when you have an outlier like that, you can disregard it from the data, and particularly if you have a real reason to do that. In this case, we know that a couple of pennies were made of plastic, and they should be falling out of the line of the rest of our data. All right, now let's focus a little bit on the blue line here. This blue line, you'll notice, is it's accurate, and that's because if you look at the y-intercept, it intersects at the origin 0, 0. But compared to the red line, the data points are sort of fluctuating from the line of best fit. So this line would be accurate, but not precise. All of those things can be told at a glance by just looking at these graphs. And again, you don't need to have done the lab to actually know which line is more accurate and which one is precise, etc. So it's pretty cool when you think about that. Another thing, and this is a major point here, that is that if you find the slope of that line, like for example if you found the slope of the red line, even though the information here is inaccurate, the slope of the line is not affected by where it hits at the y-axis. That means when we calculate the average mass of those pre-1982 pennies, the inaccuracy that's in that data is taken away. If you had used the data information itself, the data measurements, your values would be inaccurate. But if we use the slope of the line, it takes away that inaccuracy. And if you think about it, that's pretty cool. We can take some information and make it correct. We can fix it. And that's one of the major reasons why we make graphs, along with all the other reasons I just told you. So I hope this helps you understand the differences between graphs that we might do in science class compared to the more exact types of graphs that we do in your math class. And hope that helps you to write up your lab as well.